Okay, folks, in this lecture we're going to take a look at analyzing exponential functions. So, first of all, we just take a look at an exponential growth system. So that's described by this equation here, this function. And remember, that's just related directly. It's the exact same as the general mathematical kind of exponential function. And k then is the exponential growth rate. So k is crucial. K is the engine of the function. Typical curve looks like this. And now we're just going to take a look at an example where 15 people had the flu and then 2 weeks later 95 people were infected. So we're told it's exponential, so it's governed by the exponential function, its growth, so it's governed by this function here. How many people are infected after 6 days? And how long will it take before 200 people are infected? The one thing it doesn't ask for, but it's the first thing we have to do, is we must calculate k. So in the last lecture, I manipulated this function to give us this function. And I'll be doing it again when we're looking at half-life. So I will be doing it again later on in this lecture, so you can kind of refresh your memories there either. So now, from the first stage, so don't try and answer the question, guys, until you've worked out k first of all. And the first sentence will usually give you an initial value, a new value, and the time in between them. And from that then, we calculate k. Feed these values in, and always write k then to 5 significant figures. And what this represents then, if we wrote it as a percentage, is there's a 13% increase in numbers of infected people per day. So that's what k is. It's the increase per unit time. So now we can go about answering the first question. We know k. We're just asked about t, so we don't have to manipulate the original function, because the only thing we don't know is n. So the initial value, k, and t. Feed these values in. When we round it up or down, we get 33 infected people as our answer. We take a look at the second question then. How long? So how long would suggest we need to isolate t. So from our original function, we want to manipulate to get t. And again, that I did that in the previous lecture. It's pretty much the exact same as the manipulation for k, except the very last step. Feed in the values. So again, n0 never changes. n0 is always 15. K never changes either. But the value that will change is n and t. They're the two variables really in the function. So this time we're asked how long before 200 people get infected, and k is as we calculated from before. Feed the values into the function, and about 20 days, when you round up. I just left it to one decimal place. In the journals or anything like that I'm just much more interested in your presentation of the maths. So your maths, guys, should look similar to how I'm laying these problems out here. It should be very clear. I should actually even have started with the n is equal to n0 e to the kt. You will have to show that manipulation at least once. But once you've done it once, you don't have to keep doing it. And then develop the problem. Now we take a look at exponential decay, which is the converse to exponential growth. And this is where a quantity decreases by a constant factor over a period of time. Pretty much the exact same formula as the growth. The only differences, the significant difference, is the minus on the power. The trivial difference is, for decay we use the letter M, but usually this formula is changed to kind of reflect the whatever system. If we were looking at capacitance suffers exponential decay, and the formula would look like that. And K will often change its form as well. K isn't always written as K, sometimes it's written as lambda. The main thing, guys, what you're looking for, is it a minus or is it a plus? In this case it should be a decay. So the formulas will appear in loads of different ways, but what you're really looking for is that. All the other letters will change depending on the system you're examining. Typical curve. And again, guys, sorry, actually I should emphasize, you should be able to sketch these curves or the growth curve, because often that'll be asked for in journal questions. So concentration, this is a decay scenario. Concentration of a drug in the bloodstream follows an exponential decay. Now the initial concentration is in milligrams and the new concentration is in micrograms. So I would always suggest bring all the units to the lowest value. So I would bring everything to micrograms. So we have milligrams. We want to change to micrograms. What's the difference in powers? 10 to the power of 3. Because we're going from big to small, we multiply. Remember, a big thing is a multiple of a small thing, so that tells us to multiply. So now 1 milligram is 1,000 micrograms, and now it's easy enough. 1.25 milligrams is 1,250 micrograms. So we'll be using that figure when, instead of this as the initial value. So what will be the concentration after 1 day? How long will it take for the concentration to decrease to 200 micrograms per liter? But again, guys, we can't go anywhere until we calculate K first of all. Same as before, but just note the minus. Same manipulation as before, sorry. Feed the values in from the first line. Don't use any values from here yet, guys. While you're calculating K, don't use those values. M0 is always your initial value. M is the new value, and T is the time for things to happen. K now. Stick the values in. So once we do our maths, feed these values in here. And again, write your K value to 5 significant figures. And what that represents is a 19.5% decrease in drug concentration per hour. That's your rate per unit time. That's what K is. So now that we've calculated K, we can actually start to answer the questions. What will be the concentration after 1 day? Well, T, in this case, 24 hours. Always use the same units throughout the question. That's crucial. feed these values in to our function, and after 1 day there'd be 11.6 micrograms per litre concentration in the patient's blood. How long will it take for the concentration to decrease to 200 micrograms per litre? So 200 now is the new value, K is the same. So the manipulation here is just the same manipulation as before. And as I said, I'll be going over that in a little while in this lecture again. There's our K value. Feed these into our function. And that's just a wee error there, guys. That should actually be hours. I think. Yeah, should be hours. And now we'll take a look at another different type of question. So this one, guys, is talking about a function. So I'll just let you read this and I'll talk about it. But here's a function. And what this function describes is qt. Q is a function of t. Q is the number, the quantity of cameras that an experienced employee would be able to assemble in a day. So T is in months, and it's the length of time the person has been employed after they've completed basic training. So this is our function again. So quantity versus time. How many per day of these cameras can an employee assemble? So just a bunch of questions then. How many cameras can a new employee, assemble just after basic training? So how many cameras can a person make with 1 month's training? 1 month's experience. And then how many so an average experienced person, if somebody is experienced, how many cameras would they be able to produce per day? How many months of experience? This is just about manipulation then. How many months of experience is needed to assemble 40 cameras per day? So these two are fairly easy, guys. We'll take a look. What we'll do is we'll just let t equal to 0 for the first one. And then we let t equal to 1. Feed those into our function and we see what happens to q. For part C, what we're going to do is just going, well, what does experienced mean? So we'll take a look. Oh, sorry. Don't do that. Sorry. So we kind of say, well, what does experienced mean? So we take a look, well, we let t equal to 6. 6 months experience, a year, and then 2 years. That is, somebody who's working 2 years would certainly be very experienced. And the final question, D, how many months of experience is needed to assemble 40 cameras per day? So what we have to do now is put 40 in here for Q, and then manipulate for T, or solve for T. It'd probably be more correct. So we'll take a look at each of these. So like I said, T is equal to 0 when someone has just finished their basic training and started on the job. T is 0. We feed that into our function, and just after training, somebody be able to make 20 cameras a day. With 1 month of experience, let Q equal to 1. So again, we're feeding into the original function. So after a month, someone would be expected to be making about 32 cameras a day, 31. Now we're asked, well, how many would an experienced person be able to make? So we take a look at, well, after 6 months, someone would make about 48 cameras a day. After 12 months, it'd be nearly 50. After 24 months. So we can see that 50 is kind of the limiting number. It's the limit of this function. And if we were to draw a graph of it, this is what we'd have here. We can see that with a couple of months experience, with 3 months experience, people are producing about 43. After 6 months, 48 as we saw. After 12 months, very close to 50. And after that then, this line doesn't really change. There's no real change in slope. And that, guys, would be a normal kind of thing. Like an awful lot of things have that limiting nature. If you think of any kind of exercise you're doing, no matter you have your own physical limit, there's these functions would apply to sports endeavour. Say if you were bench pressing a weight, there's just a limit as to what you can do, regardless of you keep training, you're doing everything to its max. There's always limits, and as a sports person, you're always trying to push that a little bit further all the time. So how many months of experience is needed to assemble 40 cameras per day? So we essentially need to just manipulate. Now, you could feed in 40 here if you wanted. I've kept it as n. So we're just manipulating here. First, I'll actually step it through a bit. Furthest thing away, guys, we want to get t. It's nice when the subject sits at the very end, because you can just, if the subject sits on the right, well, you just start at the left. Get rid of the 50 first, subtract 50 from both sides. Now divide both sides by minus 30. Now what I'm going to do, guys, is just multiply on this left hand side. I'm just going to multiply top and bottom by minus 1. And what essentially happens is, notice the n becomes a minus. Everything that was a minus is a plus, and vice versa. And then we just write the 50 at the front, because that's good manners in maths. So I hope you'll accept that they're the same. Now what I'm going to do, guys, is get rid of the e by getting the natural log of both sides. And here, guys, we have minus 0.5. So I'm going to call that a half. Now, whatever way you want to do it, you could divide both sides by minus 0.5 and just get your calculator. That'd be fine. I just write that as a half, and then I multiply both sides by 2, or minus 2. And that'll get rid of that. That'll turn that minus a half by 2. Gives me, and if I call it this a minus, then I'll have minus 2 over minus 2, minus by a minus, divided by a minus is a plus. And that's my answer there. So I've multiplied both sides by minus 2. And that's why there's a minus 2 appearing here. I hope that makes sense. And now we just feed in 40. Now usually, guys, actually there'd be no harm there in just feeding in the 40 at the start. And just solving it out as usual. That would make sense. So someone would be making approximately 40 cameras a day after 2 months and 6 days. Multiply 0.2 by 30. So now we're just going to take a look at, again, it's exponential functions, but it's something you'll hear about quite a lot, the half-life. What's the half-life of a drug? So the half-life of a drug, it's an estimate of the period of time it takes for the amount in the body of that drug to be reduced by exactly 1/2. So essentially, what we're saying is it's best explained by a diagram. I don't know if I have one coming up, but I will shortly. Is if someone say had 100 milligrams of drug in their system when they were first measured, somebody gave blood and they had 100 milligrams. What the half life is like how long does it take? Whoops, sorry. For it to go from here to 50 milligrams. How long? That's the question. That's the half-life. And then, say this was 20 hours. Well, then in 20 hours again, this would have again halved, so it would have gone down to 25 milligrams per hour. 2 milligrams. Sorry, not per hour. And what you get is this exponential decay curve, which looks a bit like that. Again, badly drawn, but that's what the half-life is. Yeah, that's actually repeating itself. Okay, that's just obviously my error. I didn't pick that up. Same as the sentence above. Symbol for half-life is T a half. So if this is what we're saying, if 100 milligrams of a drug with a half-life of 60 minutes is taken, the following then is estimated. 60 minutes after administration, so after one half-life, only half the drug would be left. After 2 half-lives, we would now have a half by a half. We only have a quarter of the drug left. After 3 half-lives, multiply by a half again. 1/8 of the drug is left. By a half again, and it's 1/16. So here, guys, we have 4 half-lives. And usually drugs lose their efficacy after 4 or 5 half-lives. So yeah, I think you get the idea from that. However, though, during a drug test, they could still find a trace of it. So it might be no longer kind of an active kind of drug, but it still could be traced. It's just they don't have any effect. So this is the typical graph of a half-life. So you should be able to sketch one of these. I would probably be looking for one of these in any kind of a written assessment, and certainly in a lot of the questions in the journal we'll be looking for a quick sketch. And I'm not looking for a masterpiece, but I'm looking for an understanding, that you show an understanding of the nature of half-life, and that it's always a curve, and there's always this idea, guys, of it kind of tailing very, very slowly towards a limiting point. So make sure you can draw a curve like that. Note here, it's not just a sketch. Here's one half-life. Just this is like the scenario I was trying to sketch poorly on the previous slides. So this is 3 half-lives, 4 half-lives. And you can see the numbers associated with these from the previous 25, 12.5, 6.25, 3.125, etc. Oh, don't know what happened there. So this is just saying the same. And now we're just looking at the manipulation again. What I'm going to do is just manipulate for T and then feed in these values. 50% for M and 100% for M0. So first thing we do, divide both sides by M0. Now get the natural log of both sides. Then divide both sides by minus K. and I moved the minus then up to the top, but it's still a negative term. That's the main thing. Now, this is a little bit more, yeah, I'd forgotten about this bit, but I can see now. So what I'm doing here, guys, yeah, sorry, I'd kind of thought I had reached the end and I was just going to feed the values in. But I just want to take care of this minus first. And really what I'm saying here is that's really a minus 1. And now if you remember from your rules of logs, n times the log of a is the log of a to the power of n. So I'm going to bring the n up as a power. And that's what's happening here. Now what's going on here, if you remember, anything to the minus 1, 3 to the minus 1 is 1 over 3. But if I said 1/3 to the power of minus 1, well, what that is actually is 1 over a third. Remember to flip our fraction, which just gives me 3. So really what to the power of minus 1, it's the reciprocal, and we'll look at this in later lectures, but it's the reciprocal, and when we get the reciprocal of a fraction we just flip it upside down. And that's what's going to happen here. We actually just flip this upside down, and that's what we get there. So it's a bit of kind of laborious maths. I had actually forgotten about the minus 1. I hadn't really been paying it much heed. Now what we do in here is we're going to remember m0 is 100% and m is 50%. So it decayed from 100% to 50%. We feed these values in, and I hope you'll agree then that that top line becomes, so we get t is equal to the natural log of 2 divided by k. And that's the t1/2. That's the half-life. Because the 2 is obviously from the 100 over 50 from here. And then very often lambda is used instead of k. It's the exact same thing. The maths for lambda is the exact same for k, and often you will see lambda used in the place of k. It's a very common kind of alias for k. And I'm sure you remember your lambda from the Greek letters you learned last semester. So very often they will talk of the decay constant, and that's your lambda or your k value. When it's called the decay rate, often it's given as a percentage, and to find k or lambda, you have to divide by 100 in order to use it in your formula. So just be careful. They might say something had a decay rate of 37%. You wouldn't use 37, you'd have to divide by 100, lambda. So just be careful of that if you're given the decay rate. So this is the function we just had. So the value of lambda can be calculated as before. And if we know the initial value, the new value, and the half-life, then it's straightforward enough to manipulate to get lambda. It's the exact same manipulation. Sorry, I keep calling it k. we can manipulate lambda m over m0 all divided by t a half. And remember, t a half is the half-life. So for a lot of radioactive materials, the half-life is known. Like the half-life of carbon-14 is 5,730 years. So a lot of materials, the half-life is known. So this figure is just a value that you can look up and feed into your function. Alternatively, if we know the number of half-lives the process has undergone, we can just use this function here. So the base has changed. Essentially, e to the power of minus lambda is the same as a half. So this formula I'll be using, why does it do that? I'll be using this function in later slides. This one in particular. So here we're told about, like I said, many radioactive materials, their half-life is kind of common knowledge. So strontium-90 has a half-life of 28 years, and here's its typical curve. This is the maths we were doing on earlier slides. How many half-lives have we gone along? This is your x-axis. This is just the x-axis in time. So both of these are your x-axis on the left. And this is the percentage remaining. So this then is the y-axis. And this is how much is left. So really, there's my x-axis. Even though the table looks a bit convoluted. There's my x-axis, there's my y-axis. That's given me a little bit more information about the y-axis, and that's given me a little bit more information about the x-axis. So calculate the percentage of strontium-90 remaining after 280 years. So we're going to use this function because it's quite easy now to work out, well, how many half-lives did we go through? So it'll simply be 280 divided by 28. I hope you'll agree that's 10 half-lives. Which would be the equivalent to this. So if we didn't use powers or exponents, we'd be kind of have to do it this way. We had 100 at the start, and then by half, by half, by half, by half, by half. I think you get the picture. 10 times. Or we could write it like this, which is the same as our function here. So after 10 half-lives, there would only be about 0.1% of the quantity left. But this gives you an idea then of the problem of disposing of nuclear wastes and stuff. A lot of nuclear wastes are multiples of different compounds, all radioactive. So the longest radioactive element there determines how long the thing is dangerous. And even after 10 half-lives, you can still see there's about 0.1% left. That's 280 years. A lot of these have half-lives of thousands of years. So they store them in concrete, which has a half-life of about 150 years. But anyway, that's another story for another day. So, like I said, there's just the answer to the problem we were doing. Bismuth, 210. I have no idea what these elements are. You guys have probably have more an idea than me. This is a half-life of 5 days, so this is quite a quick decaying element. Suppose the sample originally had a mass of 800 milligrams. Determine the function which would represent our mass. So essentially we're looking for, well, what's M0, what's T, da-di-da-di-da. So we'll do that first and find the mass remaining after 30 days. So determine our exponential function. So first thing we're going to do is we know the half-life, we know this value. So now we can calculate lambda because it's the only unknown in our function, but we just have to do a little bit of manipulation first. So in order to calculate lambda, I'm just going to use some simple maths first. Sorry. If you agree with this statement, sorry, that's very sensitive at the moment. 3 over 6, that's 3 over 6. We can swap across the diagonals. So I can swap the 6 and the 1. And it's still a true statement. Sorry, that should be an equal sign between them. So that's what I'm actually going to do here. I could swap the 2 and the 3. So when you have two fractions, just single fractions, simple fractions on each side, you can swap across the diagonals and it is valid. So that's what I'm going to do here. I'm just going to write the left hand side as t a half. That's just t a half, guys. That's just half-life. It's just a symbol for half-life. The editor I have doesn't make it look as pretty as I'd like it to, but unfortunately that's the best I can do. So I'm going to swap t a half and lambda, and then we get lambda over 1 is equal to the natural log of 2 over t a half. It should really be a tiny little half like that. So that's what I'm doing here. Now, as I said, I know the half-life. It's 5. So I just get my calculator. And now I have my value for lambda. Again, I keep it to 5 significant figures. So now I know lambda. I know m0. I know, well, t is a variable. So m0 is 800. Lambda I've just calculated. And this now is the function that relates the new amount to time. So sorry, mass remaining is probably a better way of describing m. Part B, find the mass remaining after 30 days. Well, we just feed in 30 then for t. And we get 12.5 grams. Alternatively, we could use the other formula. 30 days is 6 half-lives. So I could use the other formula and I would have a half to the power of 6 by 800. And it gives me the same answer. When was the mass reduced to 1 milligram? And then sketch a graph. Manipulate, so when suggests time. We manipulate our function for time. I won't even talk about it anymore. We've talked about it so much. Feed in the values. In this case, the new mass is going to be 1 gram. The original mass is always the same, 800. And K is what we calculated on the previous slide. Or lambda, I should have probably put in lambda there actually. Be more correct, the maths is the exact same. Feed these in. And it would take approximately 48 days for the quantity to decay down to 1 milligram. Draw a sketch of the function, like I said, so you should always, guys, be able to draw a sketch of whatever function you're analyzing. So this is just talking now about radiocarbon dating. And the main component for radiocarbon dating is this radioactive element of carbon, carbon 14. Oops, sorry. It has a half-life of about 5,700 years. So as we eat and stuff, we accumulate carbon 14. But then as we die, this amount of carbon 14 begins to decay, whereas the amount of carbon 12, which would make up most of our body, doesn't. Now it decays, as in the body decays, but the carbon, the compound carbon, does not decay because it's not radioactive, whereas this radioactive one does decay. So by comparing these two values, comparing the stable carbon to the unstable, you can work out how old the sample you're looking at is. There's a video on it here, so I was going to show it, but the whole thing had gone too long, so I'll post this up on Moodle. And we take a look at a typical question. So a body is recovered from a peat bog. This is some famous bog body. The Aarhus man, I think, or something he's called. So based on the decay of carbon 14, they estimate that 5.5% of the original carbon 14 has decayed. So calculate the probable age of the skeleton. So we need to kind of start with what we know. So first thing, we want to calculate lambda. And we do that because we have the half-life here. So this is exactly what I talked about the last slide. We swap lambda and t. And so we calculate lambda to be this value here. Remember to keep it to 5 significant figures. If you want, you can write it as scientific notation. But just 5 significant figures, whatever way you go about it. So now we're going to use our decay formula. This was the original amount. So we're just going to say, well, there was 100% of carbon 14 at the start, and now 5.5% of it has decayed. So that means, I'm just going through the manipulation here again. So this is just what I was saying, the new amount is this, and we worked out lambda on the previous slide. So we feed these values in. Sorry guys, I didn't discuss it there, but here's the manipulation for t. Divide both sides by m0, get the natural log of both sides, and then divide both sides by minus lambda and move the minus up. So I think we've talked about it enough. So in this case, feeding these values in, we get t is 468 years. So obviously there wouldn't be much point in opening a murder investigation or anything like that. So this is the last one now. Cell doubling times. Nearly there. This lecture is a little bit longer than I planned, but we'll keep going. So often in bioscience it's necessary to grow cell cultures from an initial quantity. So formula for cell doubling is very similar to the formula for half-life from earlier in the lecture. And essentially it just looks the same. Very often, this would be replaced by CDT, cell doubling time. And this is the exponential growth rate. So cell doubling time, guys, is essentially how long does it take for a cell culture of say 10,000 to grow to 20,000. How long does it take? That's the cell doubling time. The maths is the exact same as for half-life. The only thing is we're now starting with say 10,000 and we're asking how long does it take to double. So it's just an exponential growth function. But this function doesn't really change its sign or anything because we're still just looking for this quantity of time. What's the time difference between these? And time is always kind of moving in a positive direction. So that's why there's no change of sign, even though we're now looking at a growth scenario instead of a decay scenario as we did for half-life. I hope that makes sense. We'll keep going. So a bacterial population grows from 12 colony forming units. I think you've probably met these at this stage. To 19 CFUs in 24 hours. So it goes from 12 to 19. So we have we have N0 and N, and we have T. So first thing we do before we do anything is calculate K. Then we can determine the cell doubling time. And how long will it take to grow to a population of 5,000 CFU. Finally then, how many cell doubling times does this take? So how many cell doubling times does it take? Remember we just talked about how many half-lives did it get to something? In the exact same way you talk how many cell doubling times did it take to get to a particular value. So first we need to calculate lambda, use our growth function. We need to manipulate for lambda, feed in the values from the first line in the question. And now compute. Again, 5 significant figures. Be very careful with that, people. Just 5 significant figures all the time. So, determine the cell doubling time of this bacteria. So, we know lambda. So it's just a straightforward case of calculating. And the cell doubling time is 36.2 hours. So this formula is the exact same as the half-life formula. So we've now got the cell doubling times. So each type of bacteria would have a cell doubling time. It would be a known factor in the exact same way as radioactive materials would have known half-lives. Particular cultures of bacteria would also have known cell doubling times. So we've done most of the maths now. This is fairly straightforward. How long will it take to grow to a population of 5,000? Well, we need to manipulate for T again. 5,000 is the new value, 12 is the N0, and we know lambda. Feed these in. So it'll take 315 hours to grow to a population of 5,000 CFU. Finally then, how many cell doubling times does this represent? At least we get to finish up with some fairly straightforward maths. 315 hours to reach a population of 5,000. So how many cell doubling times is that? We simply divide it by the cell doubling time. And we get, it takes 8.7 cell doubling times. So now at least a scientist can figure out, well, when do I need to start inoculating and growing my culture if I want to do a trial or a test or an assay or something on Tuesday week. When do I start inoculating so that a Tuesday week I'll have 5,000 bacteria, enough for me to do whatever I need to do? So we'll finish up there, guys. Thank you very much for listening, and I'll stop talking now. That was a long one. Okay, thanks again. Bye bye.